you to the organisers for the invitation to speak at this conference. This is a joint piece of work between myself and Professor Nigel Topham, who is my PhD supervisor at informatics at the University of Edinburgh. As Moore's law and Nernst scaling is coming to an end, this is leading to the construction of more specialized accelerator designs, which contain ever-varying different types of accelerator. However, there's tension between very fast, inflexible accelerator designs and very flexible pure software designs. This project's aim was to investigate the middle ground between these two extremes. This slide is about the background of the paper. The area that was chosen to investigate was wireless radio. It's an ever-important technology that's used today, where it's often the only communication option available on modern devices. But, however, wireless radio usually requires specialized hardware. This is mainly due to the high sample rates it operates at, and this work also needs to be performed in real time. For example, a missed deadline will cause, for example, a phone call to drop out. Also, this work involves complex signal processing mathematics, such as fast Fourier transforms and various types of filtering. It's just one example of the many different types of data streaming area. Here we talk about current radio architectures in use. Unfortunately, current radio architectures tend to operate between two extremes. Either all the computation is performed in fixed function hardware or entirely in software. Additionally, there are sometimes offload engines where a proportion of the work is performed in software and then a fixed proportion is done by hardware. But these three techniques all share the same downside. Once the data is passed from software to hardware, the data is never seen again by the CPU. You can't have bits of it software, bits of it hardware. It's all software, then hardware. Here we discuss the core concept of the work. If the fixed function hardware in the design, no matter which kind, does not fit the application exactly, it cannot be used for the given radio system. Also, the implementation has any flaws or bugs, it cannot be fixed without redesigning new hardware. The concept of this work was to design a hybrid system where a normal CPU can interact with a pipeline of accelerator blocks. This would allow new components to be added to the accelerator chain, for example, to add functionality or a new modulation standard. Additionally, it could also be used to replace a buggy or broken piece of hardware that you could bypass it using software to fix the design. This concept is not about performance or necessarily or speed. A full hardware implementation would always win on efficiency grounds, but this idea could potentially improve the longevity of systems without resorting to building new hardware, which is expensive, or using 100% software, which would be even less efficient. Here we talk about various questions. This concept would raise questions such as, could this idea be used to make radio processing systems more flexible? And then could they be enhanced after the fact? For example, to add new standards. How does performance vary across this software to hardware spectrum? And then what is the power impact of this? How close can a hybrid system can this hybrid system meet pure hardware? How should this data be streamed to the CPU? And what parts of the system demand hardware processing? And which parts can be done more easily in software? Here we discuss the radio hardware design. There are many different radio standards you could choose from, such as Wi-Fi, 4G or 5G, etc. For this work, Zigbee was chosen because it is a simple standard that is open and is easy to verify using existing tools like MATLAB. Also, Zigbee has many different physical layer designs depending on the use case. Zigbee is widely used in many Internet of Things applications and forms the basis for high-level specifications like Thread. For this work, three different modulation types from the specification were chosen. It expands to 6 different subkinds of modulation, which can be seen in the figure in the top right. It can be seen that all these modulation standards share commonality, which can be seen in which can be seen color-coded in the top right figure. Therefore, a unified pipeline of 9 blocks, where these 9 blocks would be enabled, disabled, or reconfigured, could be used to realize any of the above 6 pipelines. The system in the below figure is the system that will be modified, which we see in the next slide. This is the key idea in the work. This is the key idea in the work. How should the CPU be connected and interact with this chain of accelerator blocks? In the top figure, the same chain of accelerator blocks, just shortened, can be seen. To this chain, a device called an interposer was added that sits between each accelerator block, was added at each point in the pipeline. This can be seen in the top right figure. These interposers act like a controllable valve where data can flow transparently between blocks as if it does not exist when disabled. But if it is enabled, data can flow from the block to the CPU and back from the CPU into the next block. This will allow the CPU to process or intercept data from any tap point in the pipeline. The interposer shown in the below figure consists of a pair of multiplexers and demultiplexers that allow it to be enabled or disabled, and it contains 2 pairs of double buffers, where data is stored pending transfer to and from the CPU. And then finally, an interrupt system is used where the CPU can be notified when the double buffers are either empty or there's data ready to be read. The data is transferred to and from the interposer using a DMA from the memory system using burst transfers. This slide is about how the system was tested. To realize and test this design, the Gem 5 plus RTL paper from the Barcelona Supercomputing Center was used. This allows the hardware accelerator design, which was written in Verilog, can be seen on the right of the figure, to be connected to the popular Gem 5 simulator. This also means that the simulated design is not necessarily a simulation. The code could easily be turned into real silicon if desired. The figure shows how the various elements of the simulation were connected together. The majority of the hardware accelerator is written in Verilog and shown on the right. Additionally, a Gem 5 device was also written that's used to bridge this accelerator, which in Verilog, to the Gem 5 memory system and hierarchy. Lastly, the Gem 5 simulator is configured to emulate an ARM system on a chip running Linux. Various test programs were then written that run inside this simulation to test the behavior of the system. This simulated design allowed us to easily explore the design space of the system quickly and cheaply. Here we can start discussing the results of the work. This first set of results investigated the impact of replacing a block with software. So in this first test, each block in the chain was replaced with a software equivalent running on the CPU, each of the 9 blocks on the earlier slide. This test was repeated for a range of different buffer sizes. As expected, the larger buffers perform better. This graph shows the proportion of time the CPU spends clock-gated. This is used as a proxy for power consumption, as the longer it spends clock-gated, the less power the system uses. The main takeaway from this graph is that with a large buffer size, the CPU can reach between 5 to 35% of the pure compared to a 100% hardware solution. The full hardware solution is represented by the dotted line here at the top of the figure. Along the chain of the accelerator blocks transmission, the data rate increases as the data is transformed. So it can be seen that for earlier here, where the data rate is lower, the gap's a lot smaller than later on where the gap widens. The large drop between blocks 3 and 4 here happens because this part of the system expands the data symbols into longer sequences. So the data rate can actually increase by up to 16 times here. And again, the additional drop here is for a similar reason. The filter here can expand the data, but it's also the most mathematically complex, so it's the hardest. It's hardest on the CPU there. This set of results show a relationship between the buffer size and the data rate. However, what the thing is, what the previous slide didn't show is that for the lower buffer sizes at the higher data rates later on, the system did not meet its timing deadlines in some scenarios and would underflow the buffer, wouldn't meet its real-time deadlines. So it was decided to plot the minimum buffer size that worked for a given data rate that didn't underflow, and they were plotted against each other. This relationship shows trend, and it would allow for a given system to calculate the minimum buffer size required to replace a block running at a certain data rate. In these results show how a radio standard could be added using this system as sought about in the research questions. It was seen there were a number of blocks in the unified pipeline that were only used by one radio modulation standard. Therefore, this test simulated design where these blocks that did not exist and say would have to be added by software after the fact. This plot here shows the difference in time spent clock gated compared to a full hardware solution. This again used proxy of how much the power consumption would increase compared to a full hardware solution. So in this case, lower is better. It can be seen that adding a standard after the fact has approximately 2 to 40% impact. Again, this is mostly determined by the standard's data rate. For the BPSK standards, which are the fourth and fifth plots here, its unique blocks occur much earlier, so therefore they get to run at a much lower data rate. So software replacement of those blocks is a lot easier, so they only get about 2% performance decrease. In comparison, the OQPSK standards over here, the first three bars, unique blocks occur at the very, very end of the radio processing pipeline, meaning the software has to work a lot harder to meet the higher data rate. The GPSK standard, which is the last bar here, sits in between the two. Unique blocks are in the middle, so it's a middle ground there. However, even though, of course, software replacement here would increase the power consumption, this idea is if those standards didn't actually exist in hardware in the first place. So it's still an improvement over doing all the processing in software or having to go back to the drawing board and having to create new hardware. The following results discuss the CPU performance impact caused by the system. Here, the performance of the system was analyzed. In this set of tests, all 9 blocks were replaced with software to see the impact how the system performs for all the blocks. So the proportion of time in the system was broken up into various stages for each of the 6 standards, and that's seen as colors in the graph. These stages are, the blue here represents the time the CPU spent clock gated, so it's essentially not doing anything. The orange, which is barely visible, is the time spent initializing the whole system. The green here represents time spent in various conditions each time the system is woken up. The red here represents the time spent managing and waking up from interrupts, so when the CPU has work to do. Read is not very visible here, but it represents the time reading data from an interposer. Brown here represents the time spent doing signal processing. The pink here represents the time writing data back to the interposer, and gray, it's not very visible, it represents the time cleaning up after the system is finished. This plot is used to see what parts of the system take up the most amount of time. This also shows how complex each radio standard is against each other. You can see the one here is nowhere near as, doesn't take as much time to process as say, the first standard on the left here. It was seen that the largest proportion of times are mainly taken up by I/O, such as reading or writing, signal processing, and the interrupt management. The large time here spent clock gated in blue can be ignored because that's when the CPU is asleep. It's not using minimal power during this period. The IPC of the CPU was also measured in each of the stages mentioned in the previous slide, again with each group of bars here representing a different standard. It can be seen that the CPU is very inefficient in all stages except signal processing, which is in purple, with all of the other stages reporting back IPC values that are below 1. The signal processing, however, has IPC values above 1, which tells us that even though the signal processing takes up a large proportion of the time, the CPU is actually running very efficiently during this time. In all the other cases, the CPU is not running very efficiently, wasting time. To see what is taking time in these problematic parts of the system, a more detailed breakdown that was decided to be measured. It was seen that during reading and writing, which the majority of the time is spent on cache management, the majority of the time spent reading here is spent on cache invalidation, and the majority of the time writing here is spent on cache flushing and data copying. This is required because to make sure the data ends up in DRAM so the DMA unit can copy the data to and from the interposers. So it stays in the CPU's cache. It can already be seen here in the breakdown of the signal processing that most of the time is spent on the filtering block. This is expected as the filter is the most mathematically complicated. Therefore, in a final system, this block would be the ideal to have flexible hardware implementation, as it's the most difficult to process. The CPU pipeline state was also measured in each stage. This was to investigate the reasons behind why the CPU wasn't acting very efficiently. It is seen that the CPU is stalling on the instruction cache. The instruction cache in the fetch stage. This occurs during the system calls which are needed to manage the interrupts, and when the CPU is woken up, the cache will be stale. The cache flushing and invalidation, which happens in the rename stage, which is the second bars, that's when the data is being prepared for reading and writing to the interposers in the read and write stages. And lastly, data moving and copying, particularly in the write stage, causes the load and store queues and reorder buffers of the CPU to become full, again stalling the system. This shows that the low IPC reported by the CPU is caused by the CPU pipeline not being able to advance. It also confirms as well that the signal processing stage is running efficiently because during the DSP stage in the third set of bars, the CPU is running very efficiently. It's not blocking on any sort of, it's not blocking a lot on various conditions. Sorry about that. We now turn to the conclusion. In conclusion, the system does work well. It proves that this hybrid system can be realized and also can be used to build more flexible systems. It can also, in certain cases, get close to 100% of full hardware design. However, as seen in those prior slides, there is room for improvement, which I'm working on at the moment. The IPC is very low. This is primarily due to the cost of data movement between the accelerators, the CPUs, and its various caches. Essentially, the CPU and the accelerator want different things. The CPU wants its cache hierarchy to hide the latency of DRAM. This, of course, classically training latency and throughput. However, this accelerator needs all of its data in contiguous DRAM. So efficient burst DMA transfers can be used to copy the data, to stream the data from DRAM to the interposers. It can't read data from the cache natively. Future work. This slide shows future ideas for how to improve this system. I'm working on a few of these for my second piece of work. Could more of the system state be preloaded so the CPU has less work to do when it woke up? At the moment, the CPU wakes up, has to do various things like flushes caches and stuff. Could all of this be done for it so the system, the CPU doesn't have to do it itself? Could multiple cores be used to replace multiple blocks in parallel? At the moment, only one block at a time, one contiguous set of blocks at a time could be replaced. So could this be modified so that multiple blocks could be replaced with different cores on a multi-core CPU? This would allow this would increase efficiency by letting things happen in parallel. Can we use more tighter coupling between the CPU and the accelerator? At the moment, it's very far away from the cache hierarchy that there's a lot of memory latency. So this would reduce the overhead and potentially make it reduce the cost of data transfers. Even though the DSP system works very well, it still takes a lot of time. So could new ISA extensions be used, which would make this DSP processing more efficient, therefore reducing the amount of time? Could the system call use be optimized in the system? This would help also to reduce the impact of instruction cache misses, as when the OS does system calls, when the test program does system calls to manage the interrupts and the flush and invalidate the caches. And finally, can this data streaming accelerator concept be used in areas that is not wireless radio for other types of applications? Thank you for listening, and thanks also to UKRI and EPSSC for funding this research. Thank you.